So we're now moving on to this condition called the Fulner's condition. It's basically a very combinatorial characterization of the amenability. So let's first of all give a few definitions actually. So from last time we saw that if we consider the probability on G, basically treated as a subspace in the L1 space, that's going to be weak star dense in the mean. So basically, whenever you have something that's dense, you kind of looking forward to some kind of approximation property. So this is the first definition. Let's say definition. Suppose we have a G, we always assume it's discrete. We say that G has a approximate invariant mean. So G has a approximate invariant mean. If I can basically have something that's almost invariant mean, but using only the probability space. So for every E contained in G that's finite, and for every epsilon greater than 0, there exists some probability, let's say mu inside the probability space of G, so that if I consider the maximum of all the difference between mu with this left translation, so let's just use s dot mu to denote basically that's the left translation by s, okay? If I consider this one norm, then all of them are going to be strictly less than epsilon, okay? So here s dot mu evaluated at x is essentially just mu of x inverse of x, okay? It's basically a short form for the left translation, okay? All right, so this is of course, when your G is now compact, you don't really expect your probability space to have a left invariant mean. But because it's dense inside the M of G, you're expecting to have these kind of approximate invariant mean. So we're going to show this is an equivalent to the G being amenable. And really closely related is this, there are two conditions due to Fulner. So first of all, we have the Fulner's condition. So we say that G satisfies Fulner's condition. Let's just say this is the definition for the Fulner's condition. Basically means for every E contained in G that's finite, I can say for every epsilon greater than 0, I can find some finite subset, say finite F contained in G, so that if I consider the translation of this F by this element G, some G inside E, so let's say for all G inside E, that's not going to be too far away from F. What I mean by that is that if I take their set difference, okay, so let's use this triangle. So if you recall the A triangle with B is, if you're from computer science, that's basically the exclusive OR. So, or you can think about it as A take away B, union B take away A, okay? So the exclusive OR, okay? Exactly one of the A or B. So basically, I will require there exists some finite set so that this translation is not too far away. So it's really close to F. What do I mean by really close to F is that there's set difference, okay? So the things that are either in exactly one of G, F, or F, that's going to be bounded above by epsilon time, well, certainly depend on size of F, so epsilon time the size of F, okay? So this is if G satisfies for every finite G, E, I can always find a finite set F that satisfy these conditions, then we say satisfy the Fulner's condition. And closely related to Fulner's condition is called the Fulner's net, okay? So a Fulner's net is basically a sequence, or yeah, I should say a net of finite subsets. Let's call them F alpha, okay? So each of the F alpha is finite, so that if I consider for every G inside G, if I take their translation, so G of F alpha, I take their set difference with the F alpha, it's going to be, well, from the closely related to Fulner's condition is basically if I divide the F alpha, that's going to be small, so I want this ratio to go to 0 as along this net, okay, as a limit over this net. All right, so if I can find such a finite subset, then I say this is a Fulner's net, okay? So the big theorem we're going to prove is that all of these definitions are going to be equivalent to being amenable. So the following are going to be equivalent. So the first being G is amenable. The second being G has an approximate invariant mean. And third one being G has satisfied the Fulner's condition. And lastly, I have G has a Fulner's net. Okay, so G has a Fulner's net. Okay, so there turns out all of these four are going to be equivalent. Okay, so I am going to divide this proof into several videos. So let's in this first one, let's just prove one implies two. So if I have a mutability, then it's always have approximate invariant mean. So let's let M be left invariant mean. Okay, be a left invariant mean on the L infinity of G. Okay, L infinity of G. And so what we do is that because I have probability is weak star dense, so we proved from last time. So as weak star closure, that's just equals to the M of G. So because it's in the closure, so this M is really the limit of some probability. Okay, so there exists some mu alpha converging to this M. Okay, this is a weak star convergence. Okay. So each of these mu alpha is going to come from the probability space of G, or you can think about really the L1 functions, which sum up to 1 and they're non-negative. And because of that, if I consider every S inside the G, if I consider their left translation, so I do S left translate by mu alpha, okay? And if I minus the mu alpha, okay, and because that's going to weak star converge to, well, you can think about when you do the left translation, that will, well, converge to the left translation of the limit. So this will converge to the left translation of M minus M itself, but M is left invariant mean, so this is going to be 0. Okay, so I have these all of these S dot this left translation of mu alpha. They're going to weak star converge to the weak star converge to 0. But weak star convergence, well, you pretend your mu alpha coming from the L1 of G. So the weak star convergence on the double dual of L1 is basically the weak convergence in L1. Okay, so this you think about the weak star inside the L infinity of G dual, which is basically the L1 of G, the double dual. So this weak star convergence is the same as the weak convergence in the L1 space. Okay, so this is the weak converge on the L1 space. So now if I consider for every finite set E contained in G, let's say it's a finite, okay, and so now I can just fix finitely many S. So for every S inside E, I can consider all of these S dot, say, mu minus mu, where mu is in this probability of G, okay? And if I consider its weak closure, okay, that's going to contain 0, okay? That's because the mu alpha, if I put the mu alpha in there, that's going to converge to 0. And so 0 is certainly inside this weak closure. And the right-hand side is also convex, okay? So by the Harmonic, whenever you have something that's convex, the weak closure just coincides with the norm closure. So this is also the norm closure of these translations, okay? So that's they're the same. All right, so because of that, so now if I just consider, well, finitely many of them, I can do the same thing, okay? I can still do this norm closure. So if I consider if I put in the direct sum of S inside E, let's do some, because there's finite, the direct sum, you just understand is a usual direct sum under L1 or L infinite norm, doesn't really matter. Okay, you can take their direct sum where mu is inside the probability of G, and you just realize this as inside a finite copy. So here as inside E, this is really a finite copy inside the L1 of G. And you do the same thing. The weak closure is the same as the norm closure. and the 0 is going to be inside there, okay? So because the 0 is inside there, it just means for every epsilon greater than 0, you can find some mu inside the probability, so that each of these left translation minus mu itself is going to be norm close to 0, okay? So there exists some mu inside the probability of G, so that S dot mu minus mu, the norm, is close enough to 0, which is just equals to, is one norm is close to 0 or close to epsilon, so less than epsilon. Okay, this is for all S inside E. Okay, so this is basically the approximate invariant meaning.